to think about math now. So we are very happy to have Arun Ram from all the way from the other side of the earth in Melbourne, telling us about periodic permutations and Macdonald polynomials. Okay.
Thank you. Thanks for having me. It's a pleasure. And it's also, you know, I would like to, with these talks, it's such an urge to complain about the long flight and the jet lag and everything, but you know, I guess I have to do it better than that. So this is a story that started, so I guess it started because I wrote this paper about level 0 last year. And I'm very excited about level 0 because these are models for the affine Lie algebra that see characters, whose characters see Macdonald polynomials or specialized Macdonald polynomials. But then I sent the paper, two things happened. I went to a conference for Adriano's 90th birthday, Adriano Garcia's 90th birthday. And then I sent Adriano the paper because I was telling him, and he wrote back to me saying, I can't even understand what Macdonald polynomials you're talking about, even though there are Macdonald polynomials in our paper. So for the first time, I really sat down to try to explain to Adriano Garcia how I think about Macdonald polynomials. And that means that I had to read the old paper of Haglund, Heyman, and Lohr, which has been, I mean, it's something I should have done 10 years ago, but I finally have sat down to do it. So the other, it's kind of fun. So yeah, of course, this is joint work with Wei-Ying Guo, and that earlier paper was with Finn McGlade, who's now a student at San Diego, graduate student, and Yang Yang, who's a faculty member here in our department here. That's the other paper. Okay, so I'll start with the affine Weyl group. And of course, since I usually work in general type, I'm going to specify that this is type GLN that I'm doing today. I'm going to be everything is going to be GLN. So the affine Weyl group for GLN consists of n periodic permutations. And that means from the integers to the integers, property. So that means is equal to W of I plus N.
Right? Sorry, I think you cut out, so I don't see what you are writing.
Only every.
Arun, we can't see your screen.
Yeah.
Uh-oh.
I think he disappeared.
No, that's not good.
Oops, but I think
the board is too small. Yeah. Okay. Unstable, is it going to freak out again? Rough today. Group W is generated by some element up to Sn minus 1 and an element that I'll call S pi. So we want to think of it like a fancy symmetric group. So Si is the transposition that switches I and I plus 1 for I, well, let's end and let's write, and Si of J is J as long as J is not I or I plus 1. And then there's this new element, S pi. So S pi just takes I and sends it to I plus 1 for all elements, for all integers. So it just shifts everything over by 1. Okay, so now there's an action of this, the operators on the lattice. So that whenever you have an affine Weil group, there's an underlying lattice. And so I'm going to take that. So if mu is an n-tuple integer, then we can define these operators. So SI will take my sequence and just permute the ith and the ith plus first components.
Ivan, I have a question. So you say that the n periodic permutation is generated by this Si plus S1 up to Sn minus 1, but like S1 is already not periodic permutation. It's already not an n periodic permutation.
Oh, but I can view it as a periodic. I view it as a periodic permutation just by putting the periodicity in it. So I should have written that this condition is for I going between 1 and n minus 1. And then I use the periodicity to extend it. Yeah, very good. Okay, so then SI just switches the ith and I plus first coordinates of mu, and S pi, when it acts on a sequence of integers, it takes the last one, moves it around and adds 1, and then it shifts all the others over just moves them over into their spots. So it cycles around, but it adds 1 when it cycles around. Okay, so that's I'll copy this so that we have the, so that we don't lose this. All right, so now whenever I have things in this, so I'll stress this subset. So if I take a sequence that consists of non-negative integers, then I can draw boxes. And so I draw mu I boxes in row I. So the first entry here is 0, which is where I have 0 boxes in the first row, and then 4 boxes in the second row, and so on. And I'm a number, so, but actually I think of this all on a cylinder, because I'm going to put this periodicity into the game, and the cylinder actually begins 1 row earlier. So when I choose mu, I'm choosing some boxes on this cylinder, and the boxes are numbered starting 1, 2, 3, 4, 5, and then you go around the cylinder 6, 7, 8, 9, 10, go around the cylinder 11, 12, 13, 14, 15, and so on. So the periodicity is all captured when I number the box by I plus nj. So in fact, I don't have to number the boxes by their row and their column. I can just number them by a positive integer, which is going around this cylinder. Okay, so now I'm going to let mu be the minimal length element. Minimal length. With u mu acting on 0 gives me mu. Right, we have this action of the affine Weil group on sequences of integers. And so I can start at 0, the origin, and I can try to make it go all the way up to mu. And that's called u mu. And this u mu is really the hero of the story. This is our hero. Because that's what you really need to construct Macdonald polynomials. So here's an example of how you construct u mu. And in a greedy way. I want to be greedy. So I'll first move the 4 to the beginning, to the left. And then I'll apply pi inverse, S pi inverse, to move it around to the end, but then it subtracts 1. So the action of pi is this, except I'm doing S pi inverse, so it cycles it the other way and subtracts 1. It this way and adding 1. And then I've removed 1 box, and so I'll do it again. So I'll get 5, 0, 1, 4, 3. And then I'll cycle that around with S pi inverse, and that gives me 0, 1, 4, 3, 4. And then I could do the same process again, and I'll get 0, 4. So something happened here. 0, 1, 4, 3, 4. 0, 4, 3, 4, 0. And I'll do another one, S1, S pi inverse, and that'll give me 0, 3, 4, 0, 3. Does it make sense so far what this process of just being greedy and cycling around? And then of course you finish this computation. And when you finish this computation, it doesn't quite fit here. You find that this is S1 S pi to the 6th, S2 S1 pi to the 7th, S3 S2 S1 S pi. Oh, I'm writing pi, but I should be writing S pi. S pi, S pi. So I hope that makes sense. I'm just being greedy, and I start with mu, and I eventually end up at 0. And so now if I reverse the process, that takes me from 0 to mu, and u mu here, let's copy this. So u mu is the shortest way to go from 0 to mu. So the shortest way to go from 0 to mu is just to reverse this. And that takes me all the way back to mu. And that's how I get this expression for u mu. All right, one step at a time. But now we can write this in the boxes instead. I'm going to write them in order. Remember, my boxes are ordered by this red ordering. So this is my red ordering here. Let's see if we can pick up these so that they don't disappear. Yeah. So my boxes are ordered by the red ordering. And so I'll put in these entries for the reduced word 1 box at a time. Because I want to be sort of box focused. Okay, so that's the reduced word for u mu. I'm just looking at permutations. U mu is the shortest thing that takes me from 0 to mu, and now I've written down a reduced word for this. Okay, so this is the first proposition, is if you start with what's called a weak or a weak composition, I think. So if you start with something that's all positive, for a box, so box is, I'm going to define this constant. So this is the number of I prime between 1 and I minus 1, such that mu I prime is less than, let's see, less than mu I and less than j, and plus the number of I prime between 1 and between I plus 1 and n, so bigger than I, such that mu I prime is less than or equal to j minus 1 is less than mu I. So that's some number. And now I'm going to take the sequence that is S mu I U mu ij all the way down to S1 and then S pi. And so the point is that this gives you now a combinatorial formula, so I can write a product over all the boxes in my shape mu of these sequences. So I've got a sequence, decreasing sequence, just like we have here. This is B, and what are we looking at here? So this is one, the fifth row and the second, sorry, B5 plus 2 times n. So that sequence is this sequence that I'm talking about here. And if I take all of the product of all of these in increasing order, that's a reduced word. Okay, so that's the first result. We can actually write down physically this reduced word in a very combinatorial framework.
Sorry, I have a question here.
Yeah.
So I thought that U mu is just a number, which is the minimum time where you can go from one to the other. But now U mu is now a reduced word. So that's what I don't understand.
So I should say this better. This is the minimal length element of W.
Oh, okay.
So let's make a new version of that one too.
I see.
So I'm taking the affine permutation, the periodic permutation, which is of minimal length, that takes 0 to mu. And then I'm trying to write down a reduced word for this U mu. So my favorite reduced word. And this box greedy reduced word is my favorite one. This is the one that was used if you do Macdonald polynomials, this, or Jack polynomials, or this kind of stuff. This was the one that was used by Knoop and Sahi, and then again by Hagelin, Heyman, Lohr. I mean, they didn't say it. Yeah.
So just to say, so how does this picture? How does this picture of this mu get into this your description? Like, is it? I mean, I think it doesn't seem to me that you actually didn't need to use this picture in the the time when you fill in the elements into the boxes.
Well, okay. I use the mu to calculate this. This is the mu that I start with. And then I do this process to produce this reduced word.
Okay.
So and that process is doing it box by box. So it's really producing these sequences one box at a time.
I see. I see what you mean. Yes. Okay.
And so the proposition then is just a combinatorial way of telling you what the answer is after that process. So this is a description of the Knoop-Sahi reduced word. Except that they didn't say anything about affine permutations, so you have to do that conversion yourself. Okay, great. So now let me talk about inversions. So inversions, let's let W be a periodic permutation. B. Well, an inversion should be a pair, we hope, JK, and we want J to be less than K and W of J to be greater than WK. But of course, now this pair can be any pair of integers because W is a permutation from the integers to the integers. But it's periodic. So the fact that it's periodic means that if JK is an inversion, then J plus N, K plus N will also be. All right. So we don't really want to think about that. So what we do is we'll assume that J is fixed between 1 and N. And that's a good thing to do because at least if you're me, you have to always think of some affine Lie algebra in the background. I can't think without root systems and so on. And so what I'll do is I'll take this inversion, so not K, sorry, Ln. This is my inversion JK now. And I'm going to rewrite that in root system notation. So in root system notation, this is epsilon I check minus epsilon J check plus L times K. So this would be, we don't have to use root systems, but this is the connection to the corresponding affine Lie algebra. So it's actually a co-root, this inversion. And then when you're in the world of affine Lie algebras, there are two statistics that are absolutely essential. There's the height and there's the shift of this affine root. And the shift is the L and the height is J minus I. So these are the, in root system worlds, you would get these two statistics. Okay, so I'm going to think about inversions. I'm going to put this extra condition when I talk about inversions so that I get rid of the periodicity in the inversion set. I don't want to have too many. There's no need in keeping the extra inversions. Okay, so now we can write down another theorem, another proposition. So again, I'm going to start with a mu with non-negative integer entries. And if I take a box in that shape, I'm going to define now this constant. So this constant V mu I is the number of entries, number of rows before I, such that mu I prime is less than mu I, plus the number of entries after I, such that mu I prime is less than or equal to mu I. And then I think I have to add 1. Okay, so that's, again, some number you calculate. And now I'm going to define R mu ij. So R mu ij consists of epsilon 1 check epsilon V mu I check plus mu I minus j plus 1 times k. And then epsilon 2 check minus epsilon V mu I check plus mu I minus j plus 1 times k. And you keep going all the way up to this number, u mu ij, right? U mu ij is this same number we defined here, this number, minus epsilon v mu I plus mu I minus j plus 1 times k. All right, so all those roots.
Sorry to interrupt again, Arun, but I don't see a difference between the R mu ij. I don't see a difference between the first number and the second number. What is the?
This is an epsilon 2. So these go 1, 2, 3, 4, all the way up to u mu sub I.
I see. So and the rest of the stuff is the same.
And the rest of the stuff is the same. That's exactly right. Yeah. Okay. So once you've made these definitions, then the point is that if you want to look at the inversion set of this element u mu, then that is the union over all the boxes in the shape of R mu ij. All right, so we've collected up exactly what the inversions are. I think I have a picture here. I don't need this. Yeah, so here's a example. So this is the same mu 04514, and I've arranged in each box the set R mu ij. And so you can see that you've got increasing 1, 2. Actually, this is a typo. This one should be 2. Sorry about that. But then 1, 2, 3. They should be increasing 1, 2, 3 on the first index. The second index always remains the same, and the distance, the k, the shift here, 2k, 3k, 4k as you move down the leg of them. So that's what. So this was just some exercise. We're doing this exercise in periodic permutations. We've got this favorite periodic permutation u mu, the box greedy one. And then we've written down a reduced word for it, and we've written down the inversions of it. Okay. So
Arun, so just to make sure I really understand, but I think that there's also some typo, right, in the box at the rectus box.
yes, there should be 1, 2, 3. This should be a 3 here.
Yes. Okay. Then
and this should be a 2 here. There's quite a few typos. This should be a 2 here. Yeah. I was making this table in a hurry. I should have. But I think the proposition is stated correctly.
But then have you defined what is the inversion? Is this a definition of inversion of u mu, or is it just I forget, but
inversion of mu, inversion of w is this thing.
Yes, but this is the inversion of a word. Okay, so inversion.
So this is an element w in w, and u mu
is a word. Okay.
Is a periodic permutation such that u mu acting on 0 is mu1 up to mu n. Okay, so that's my inversion set.
So somehow the JK is a they are pairs of numbers, but somehow the one that you write inversion of u mu, yeah, I see. But the inversion of u mu that you write is an element in the is an element of roots. I see. But you do the correspondence. Okay, got it.
This is the correspondence I want to use. Yeah. And the reason I want that correspondence is because of these two things. Because I'm thinking a little bit about the affine Lie algebra, and I want to have this height and this shift available. So for every one of these roots, there's some statistic on the affine Lie algebra, which is related to the height and the shift of these roots in this table. Okay.
Question. So could you explain why, like usually for affine Lie algebra, so you pick the other, like when you deal with Coxeter groups, the other permutation S pi should switch kind of the first and the last, like 0 and -1 or something like this. And then you have this element that shifts everything by 1. Does it have what is its root theoretic meaning of that S pi element?
So S pi is, yeah, so you're talking about an additional element, you're right, which I would normally call S0. And S0, let's see if I can write it, takes 1 to, S0 takes 1 to 0, yeah, and S0 takes 0 to 1, and it takes, and S0 will take I to I for I between 2 and n minus 1. So that's the element which is called S0. And I agree that usually, because you want to make the affine-Dinkin diagram, you would usually consider this as 0. But in GLN, you have this S pi available also. And if you put S pi in, you can get rid of S0. If you put S0 in, you can sort of get rid of S pi. So the GLN people prefer to work with S pi.
I see. I've just never seen people talking about inversions and reduced words with respect to a system that's not a Coxeter system, you know. It's a little...
But this is a Coxeter system, except that it's got this, I mean, there is a corresponding loop group associated there. So GLN C TT inverse, or double bracket T maybe is. So there is a corresponding loop group. That loop group has a root system, so you can always talk about inversions and so on.
Okay.
Okay, great. So so where are we at? Oh yeah, so we've written down this proposition which finds the inversions of U mu. And I must have copied it here. Yeah, there we go. Okay, so now we can come to the main point of this talk. So the main point is that there's this formula of Hagelin-Heyman-Lohr. And the formula reads like this. It says you take the sum over all non-attacking fillings of mu. You take x to the t for that filling. You take q to the maj of that filling. You take t to the COVID statistic of that filling times the product over all boxes in the shape t of ij not equal to t of ij minus 1, and then 1 minus t divided by 1 minus q to the leg of ij plus 1, and t to the arm of ij plus 1. All right, so this is non-attacking fillings of mu. And then all of these, this is called the leg of the box ij, and this is called the arm of the box ij. And if you do this kind of Macdonald polynomials, you know these statistics upside down and backwards. But I did not know these statistics until I started reading this paper. And
wait,
the point.
Can I ask a question?
Yeah.
I don't know the COVID statistic.
Oh, I'm sorry. I'm sorry. That's my Freudian slip.
Yeah. Okay. I was gonna say.
Because I don't like this Cohen statistic,
Yeah.
and so at some point with my students I started calling it the COVID statistic, and now
Okay, that's what I figured, but I was want to make sure.
Yes. Okay. Good. So the point is that if we take these, this is my set R mu ij, which is this list of roots, and if I take the height and the shift of the last element here, so this last one, which is in this table, if I take the height of that, I get the arm, And if I take the shift of that, I get the leg. All right. So these two statistics that are appearing in this part of the formula are exactly given by this process. Take the U mu, take its inversions, and take the last one in the set, and then those are the statistics that are appearing. And we have now figured out similar interpretations for these others, but those are more complicated. And so I decided not to present them. So, but this is the way that I'm trying to make these two statistics natural and get them just from periodic permutations. Okay, so I thought because this formula for Macdonald polynomials, if you work in the business, then that's your friend. But if you don't, then it's not so pleasant. And so I wanted to explain where this comes from and how I would derive the connections that I'm talking about. So for polynomials, so I'll go back and tell you what I'm going to do now is go back and tell you what the Macdonald polynomials are, where did they come from. So for polynomials, you can make a monomial, a short notation for a monomial, which is you take this sequence of mu's, and then you just take x1 to the mu1, xn to the mu1, and you call that x to the mu. And when you do that, that turns this abelian group from an additive abelian group to a multiplicative abelian group. So x to the mu nu. And then your polynomial ring has a basis indexed exactly by these non-negative integers. So for me, first of all, is these mu's, this lattice, is a basis of a polynomial ring. And if I were to take the smaller polynomial ring, that's got a basis which is indexed by these weak compositions. So when you're reading those papers, you can think about, okay, when we say let mu be a weak composition, that's the same as choosing a favorite basis element for my polynomial ring that I've got over here. Now the affine Weyl group naturally acts on these rings because I can just make SI, the way I've defined it, I can make SI x to the mu be S x to the SI mu, and S pi x to the mu be x to the S pi mu. So the periodic permutations will act on polynomials. That's a completely general type phenomena. Now, the key thing is that I want Daha. So to make Daha, Daha stands for double affine Hecke algebra. And this was the great construction of Cherednik to tell us how to think about Macdonald polynomials in a powerful way. So you need, first of all, you need two constants. And I want to choose those so that one is not a power, so that q to the s, qt to the h is not one. Well, ever, except when, unless it's q to the 0, t to the 0 is of course 1. But just choose two numbers that are not algebraic in that sense. Now we can define operators on the polynomial ring. So sigma pi, let's see, I have to get straight which is which here. So sigma pi is the operator t to the minus a half times n minus 1 times x1 s1 up to sn minus 1. And these capital S's are given by formula. This is t minus txi minus xi plus 1 divided by xi minus xi plus 1 times 1 minus si. So this guy looks kind of like a divided difference operator. So this is a deformed divided difference. And you can see that this sigma pi is trying to increase x1 by 1. Increase the power of x1 by 1. And then this part is doing the cycling. Cycle. So these are some deformed versions of the operators I gave you before. And this last one is little s1, s2, up to Sn. So those are just ordinary permutations of the monomial. And then this translation operator. And this translation operator appears in Macdonald's book. So in Macdonald's book on symmetric functions. So this is, for symmetric functions people, this is a more familiar operator. It just takes the last variable and multiplies it by Q inverse everywhere. So everywhere you've got an xn in your polynomial, you put Q inverse xn in that spot. Okay, so these give you some operators. And the action, so now you get an action of a bunch of operators on the polynomial ring. Now, from this, you build these Torednik-Dunkel operators. So the Torednik-Dunkel operators are given by this formula in the way that I've normalized. I minus 1 minus a half n minus 1. And then S, these are capital S's now, so I'm using all of this Daha action. Sn minus 1 down to Sn. An amazing thing happens, and that is these guys commute. These yi's. So that was so in the world of integrable systems, that's when you get all excited because you've got a whole bunch of operators that commute. Now the intertwiners then are given by the following formulas. You take Si plus 1 minus t divided by 1 minus yi inverse yi plus 1. And sigma pi is sigma pi like we defined before, the same sigma pi that's up here. Okay, so I've got a whole bunch of operators, or I didn't really have to have a whole bunch. What I really want is the intertwiners, and I only defined the other ones, these intertwiners, and I only really defined the other ones because I needed them, the other ones, to get to the intertwiners. Okay, so now I can tell you what Macdonald polynomials are. So mu again is a sequence of non-negative integers. And lambda is going to be the decreasing rearrangement of that. So lambda feels like a partition. It's still a sequence. I could keep the zeros in, but it's a decreasing rearrangement.
I'm sorry, for the intertwiners, is it clear that they produce polynomials given a polynomial?
It's not difficult. I mean, given what I've said, it's not trivial, but it's only about 4 or 5 lines, so it's not. Yeah.
Thanks.
Okay, so now I'm gonna this z mu is, you want to take lambda and you want to rearrange it to get mu. So I presented it the other way. It sounds funny. I started with mu and then told you to take lambda as the decreasing rearrangement. And now I'm going to take lambda and rearrange it to mu. That's what z mu is. And then I'm going to choose a reduced word for this permutation. So this is just an ordinary permutation in the symmetric group. All right. And I'm in it. Now, remember, this is my hero here. This is the reason for the first, why I started considering U mu in the first place is it's coming up in Macdonald polynomials. So I'm going to choose a reduced word for this U mu, which is what we did in the first half of the talk, was choose a reduced word for this U mu. This is a periodic permutation. Exactly the same as from the first half, as before. Okay, so that's the data I've got. The really important parts of the data right now are this one and this one. So now I can tell you what this what the non-symmetric Macdonald polynomial is. The non-symmetric Macdonald polynomial is t to the minus a half. This is a normalization. Lambda I minus lambda j summed up. So that's just a constant out in front. And then I take the intertwiners and I apply them in a sequence to the polynomial 1. I mean, I could write 1 if you like. I could change the x to the 0 to 1, but that's the origin. You start there. And you apply these intertwiners exactly in the same sequence from your reduced word. So now hopefully it makes sense. Why did I do what I did at the beginning when I have to analyze this U mu? Because if I don't analyze this U mu, I have no chance of understanding this Macdonald polynomial. At least that's my philosophy. Okay, so now in the combinatorial literature, there's some other kinds of Macdonald polynomials that have appeared. So one of them is this F mu, which is called the permuted basement Macdonald polynomial. And F mu is E lambda, and then I apply the capital S's exactly according to this sequence for Z mu. All right, so that's, and there are combinatorial formulas for permuted basement Macdonald polynomials as well that look very similar to Hagelin-Heyman-Lohr. So in particular, this is Alexanderson, Ferreira. I don't know. There are more. Oh, Cortil. These are the ones that are being studied by Cortil, Mandelstam, Williams. And they have a very nice connection to the ASEP, the asymmetric exclusion process. So they are, if you think about the ASEP in terms of polynomial actions of the Hecke algebra, then these F mu's are exactly the multi-species ASEP basis for that action of the Hecke algebra. And finally, the symmetric Macdonald polynomial is the sum of these F's. As you run over rearrangements, so this is rearrangements of the partition lambda, and that gives you the symmetric Macdonald polynomials, which were the original ones that started the whole subject of Macdonald polynomials off, that Macdonald defined in about 1985. That's these guys. Something like that. So hopefully that tells you why I wanted to think about this, and also why the study of this reduced word and the inversions of U mu would give statistics that would be relevant to Macdonald polynomials. And I haven't told you about the COVID statistic and the major index, but they can also be written in terms of this combinatorics of the special element U mu. All right, I think my time is up, so I should stop there. Thank you.